Cool. All right, everybody's on the record officially now. So welcome all to the December Appalachian Trail Golden Packet Knowledge Share. So this is our fourth. Let's see how good my math is. I think this will be our fourth.
Yeah,
So yeah, fourth knowledge share session, and they seem to just keep getting better and better. So
I normally have a conflict this night, but I blew that one off because John's here talking tonight. So
see, there you go. So John, you got people that are reprioritizing because you're presenting, so no pressure. Anyway, so you know, I won't really do any formalities or anything like that. So I'm actually just going to hand it over to John WB2OSZ, who just joined Golden Packet. Was it back in July-ish time frame? So he's been kind of hanging out in the wings and seeing what we're up to. And I thought Direwolf would be a great topic for a knowledge share. So John, I'll just hand it over to you and go on mute. And are you able to share your screen, or do you need me to give you permission?
Let me see.
So down at the bottom, share screen. Yep, there you go. It's coming up.
There we are.
Fantastic. All right, so we see PowerPoint.
Okay, I'm going to turn off the camera though.
Yeah,
So,
yeah, guys, if you're on video, go ahead and stop your camera.
How do I do it? Stop video. Can you still see the
Yep,
screen?
still see your PowerPoint. Yeah, you probably just want to maximize it, maybe go into presenter mode.
Beautiful.
There you go.
That's
Excellent.
good.
Okay. All right, so thanks for the opportunity to talk about my favorite subject here. I'm going to start off with a little bit of history about packet radio and what is a TNC. I know this is a very experienced crowd, so I'm going to zip right through it really, really fast. But I don't want to skip over it entirely because I think there's a couple important points in there. The main theme will be replacing, or rather the evolution from the old hardware specific TNC with an only software solution. And I want to spend quite a bit of time on what it took to build a better demodulator. That's a topic that often seems to be glossed over. So this is how we sent text before we had personal computers. Okay, who's ever used one of these?
listen to him, never used them.
That's what John Tarmac still has in his house, actually, in Maine. I'm just kidding.
Okay, so teletype machines were first created back in the 1930s, and as soon as they showed up in the surplus market, hams put them on the air, just using a simple modem known as a terminal unit. This was not a really good way of doing things. You turn on the transmitter, and the signal from the keyboard would go straight out to the transmitter real time. Not a good way, no error detection. So around 1978, some ham radio operators in Canada came out with a brand new concept of sending the information in short packets rather than a character at a time. So they put together an old modem and a microprocessor controlled unit represented by the brain there to provide some intelligence to the process. So now, rather than having the keys go directly onto the air real time, you can then accumulate a message and then send it out as a brief burst. this has many advantages. Rather than having your transmitter on for a long time, you just send a short burst. Each packet has addresses of where it came from, where it's going to. This allows many people to share a channel. There's error detection, and for the connected mode, there's automatic acknowledgement and retries. So you have reliable, reliable transport, or you get an error indication that it failed. So the Vancouver group made their TNC available as a bare board, and this did not gain very much popularity because it was a lot of trouble to gather up all the parts.
I couldn't imagine why. Yeah.
Yeah. So everything changed around 1983 when the Tucson Amateur Packet Radio came out with their TNC1 kit. So here we have one of them. What's it, serial number? I don't know, 244 is it? If I look closely. And then, so this made things really easy. It had absolutely everything you needed, except for the metal case. And of course, a couple years later, they came out with the TNC2, which was smaller, simpler, and cheaper to produce. Now, the interface was designed around a person sitting at a dumb terminal. And so it's kind of hard to unravel what some of this stuff is. So text sent to the TNC could be commands to the TNC, or it could be a message sent to another person. Text coming from the TNC could be just monitoring of the channel. It could be echoing of commands, messages from the TNC, or messages from another person. So when people, started to write computer programs to drive the TNCs rather than using dumb terminals, it was kind of difficult to unravel all this. So this led to the KISS protocol, okay? And this allowed you to have a TNC, which was very, very simple. The computer did all the work of building up the packet, so it needed to know all the intimate details of the protocol, and then the TNC would simply add the HDL structure around it with the framing and the checksum.
Was just out of curiosity, the interface to KISS from a PC standpoint, is it always over TCP/IP, or was there anything else before?
No, it was originally an RS-232 cable.
Ah, okay.
Because that's all they had back then.
Very nice.
Right? There's no USB.
Wasn't the WADED protocol the precursor to KISS too? Protocol.
There were some variations on it. There was something called 6-pack. There were different variations on the scheme where you'd put the smarts in the computer, and the TNC would do a little more than wrap it up in HDLC.
Right, you're showing these old TNCs, and I'm thinking, oh yeah, I've got a boarded GLB downstairs. I've got a Tapper 2 TNC downstairs. I'm kind of old in this group already.
Okay, so for a while, everyone was building TNCs. There were bulletin boards popping up everywhere. But then when the internet became generally available, people seemed to lose interest in doing bulletin boards over the air. So then along comes APRS, which is a good use for all those old TNCs that were not being used anymore. Now, it's important that APRS is not a vehicle tracking system. I think the inventor WB4 APRS, no, WB4 APR, APRS, that's the plural form. He liked to refer to it as something like a tactical real-time information source for local situation awareness. And APRS has a lot of potential, but unfortunately we're not using a lot of it. Okay, so end of the previous century, the accepted way of doing things was to run out by a TNC for about $200 and then connect it up to your computer, which is often running just a terminal program. But since you have a computer, which is a lot more powerful than the microprocessor inside the TNC, it makes sense to just eliminate the TNC in the middle and move it all into software. Everybody uses this for FLDigi and FT8, but for some reason, some people just have a mental block about using it for packet radio and APRS. Okay, this gives you tremendous flexibility. So you're no longer, let's see, do I have a mouse here? Yes, I do. So you're no longer restricted to having access to one radio and this, RS-232 cable. Now the software TNC could be used by multiple radios at the same time and talk to multiple applications all at the same time: Bluetooth, Wi-Fi, Ethernet, weather stations, all at the same time. I think the answer to this. Direwolf is, a free open source software replacement for the traditional TNC.
John,
So
just a quick question as far as KISS is concerned. Can you go back to the last slide for a moment?
Sure.
So, with respect to multiple devices or multiple applications on a device, all pointing to the same TNC, is there anything in the KISS protocol to prevent contention for the TNC? You could have multiple applications all trying to utilize it at the same time, right? Potentially.
No, if everyone is going over TCP, there's no problem at all. Everything can go at the same time.
Okay.
There is.
I was just wondering, I guess as far as so the TNC is ultimately interfacing with the radio, right, over RF. So.
Yeah, but we have a modern operating system and it's all multi-threaded. So there's all sorts of stuff flying around at once.
And depending on how you're implementing things like Direwolf, you can have one radio on the left channel and one on the right channel. So you have radio.
Well, even beyond that, you can have
multiple sound
up to 3 audio interfaces and up to 2 channels each. You could have 6 radios, or with a single line change of the source code, you could bump that up to a bigger number.
Wow.
Okay, so I think you know what it is. Runs on many different operating systems. Without any additional software, can be used as a GPS tracker, digipeater, internet gateway, Aprs-Tt gateway. That's Keith's favorite. And it can be used as a virtual TNC for all the applications that can talk to a traditional TNC. And of course, at the time when I started thinking about names, I could have called it something like soft TNC, but that's really lame. So I just started juggling words around and came up with this. So here's an overview of all the functionality. Don't try to read all the words. We'll revisit most of these, but the things to notice are down at the bottom. We have radios, both traditional radios and software-defined radios. We can send AX25, FX25, and IL2P that has forward error correction. And we have a variety of modems, touch tones, speech synthesizer, Morse code. Then above here, we have different ways of producing and consuming the packets. And up at the top, we have external sources or sinks of data, GPS receiver, weather station, internet, and the applications, which can be connected by good old serial port or TCP, Wi-Fi, Ethernet, or Bluetooth. So here are some examples of sound interfaces that could be used. The one interesting thing here is this little USB audio adapter. And if you look carefully, you'll see there's a couple wires sticking out of it. And the reason for that is that if you have a chip in there made by C Media, there are extra general purpose IO pins available, which software can control. And then we can use that for the push to talk signal. So that makes a very tidy solution. You have a single USB connector for both push to talk and the audio. And there are numerous interfaces like, was it Dyna, which use that chip and have some extra circuitry so they connect straight to transceivers. It can also be used with a software-defined radio. There's a couple different ways to get audio from the SDR software into Direwolf. And does anyone know what sort of modem is specified in the AX-Tt25 protocol specification?
Is it the Bell 202?
Wrong. Okay, go read the AX-Tt25 protocol spec, read the APRS protocol spec. Nobody ever says anything about modems. The reason we're using the Bell 202, according to one of the early Canadian experimenters, is they obtained a big pile of old Bell 202 modems for 75 cents each.
Telephone modems, yep.
Okay, so rather than building their own modems, they just use that. Is a cheap, quick, temporary method just to get something up and running. And here we are, what, 40 some years later, and here we are, still using the same old method.
It's just like the railroad tracks are the same width as a Roman chariot cart, right?
Yeah, I guess once you start using something.
Nurse is a tough thing to overcome.
Yeah. So, most of these look familiar to you. I also like to point out that Direwolf also has a demodulator for AIS, which is the commercial system for tracking ships. So if you live fairly close to the coast, you can pick up those signals. And then there's a built-in converter that will change them to APRS objects. So then you can display them on the normal APS applications. There's also a demodulator for the emergency alert system, and we'll get into that later. So we're normally using radios that were designed for voice, not digital data. So voice is generally considered to be like around 300 to 3000 hertz. So if you're using the microphone and speaker connections, it's very important that you use frequencies only, well within that range. And the original 1200 baud fits in there nicely. Now, MFJ, AEA, and Cantronics all came out with TNCs that supported twice that speed using phase shift keying. And it uses just about the same amount of bandwidth. And in my experimentation, it works great with all combinations of speakers, microphones, and flat audio. So I guess if a couple more manufacturers adopted that, we might all be using 2400 these days. Now, the 9600 is an entirely different beast. This is the same scale here. See, 3000, 3000. To make this work, you need bandwidth out to about 5 kilohertz. Okay, I think most people are familiar with that. But the other thing that's never mentioned is this also requires very low frequencies. And if you take audio from the speaker, it'll cut off frequencies below about 300 hertz. So you don't hear the PL tones. Okay, I think everyone's familiar with this. So to use the higher speeds, the big 3 Japanese manufacturers all standardized on this one connector that gives you, wide bandwidth flat audio, straight from the discriminator, and the transmit audio is, also bypasses the normal circuitry. This is the first time I tried this. Does that sound familiar?
Yeah, it was kind of hard to hear.
I didn't hear much of the audio.
Yeah, I heard a little bit of the weather alert.
Yeah, I wasn't sure how that would work if there was some sort of cancellation that something coming out of the speaker wouldn't get fed back into the microphone. I'll do it again.
Oh yeah, there's actually there is a setting to include the computer audio when you do the sharing.
Oh well.
Okay, I thought, I'm like, geez, I didn't hear that. Okay, that makes sense.
Okay, so anyhow, the national, moving along, because we've got a lot of material here. The National Weather Service has more than 1,000 stations, that are constantly transmitting weather information around 162 megahertz. And whenever there's some sort of emergency condition, they will transmit digital data as well as voice. And sometimes on TV, you hear the announcement of, this is the weekly test of the emergency broadcast system. I think that's the same encoding, but I'm not sure. So you can connect 2 radios up to Direwolf, and the weather receiver could even be a $20 software-defined radio. It can then decode this information that goes over the air. And then there's an included script, which I call EAS to APRS, that takes the emergency alert system and then translates it to this plain text. And then it gets sent out and transmitted over the APRS radio as an APRS bulletin. So I found that interesting. Maybe other people could find a use for it. Direwolf can also send and receive DTMF, commonly known as touch tone. There are dozens of free speech synthesizers available where you just give them plain text and outcome synthesized speech. So if the destination address is set to speech, it does not get transmitted over AX25 the way it normally would. Instead, it invokes a user-defined script, which you would normally use to invoke a speech synthesizer. So here's an example. You could have a beacon sending it to speech and say, club meeting tonight at 7 p.m. And that would get transmitted over the radio as speech. Interesting possibilities there. You can have systems that, could respond with speech. Can also send Morse code. You know what beacons are, right? It's just periodic transmissions. If you get information, you can get information from external sources like a GPS receiver, telemetry data, weather equipment. There's also a Telemetry Toolkit. This is just a collection of documentation and some scripts that allow you to put together custom solutions for telemetry. And there's even a complete example in there where a Raspberry Pi is connected to an analog to digital converter, and the voltage is then converted to APRS telemetry. Okay, who knows what an Aprs-Tt gateway is, other than Keith? No? Okay. So the reasoning here is that not too many people have portable equipment for operating APRS, but almost everyone has a handheld with a touch tone pad on it. And this is a method that people can use that touch tone pad to enter information into the global APRS network. And this is not a new idea. There were implementations going back about 20 years, but they were based on specialized hardware and they were not too flexible to adapt to new situations. So I threw in my implementation of this old idea. And this is an example of where you could use it. Supposing there was a canoe race and you didn't have enough budget in order to put an APRS GPS tracker on each of the canoes. What you could do is you could have observers at different checkpoints along the way and assign a number to each of the canoes. And then a person standing at checkpoint number 3, when canoe canoe 12 goes by, the person at checkpoint 3 would key up his radio and punch in 3 for the location, 1, 2 for the object or the canoe number. This gets picked up by one radio. It goes into the gateway for processing. First, it responds with synthesized speech to that same channel. And it says canoe 12. The system then generates an APRS object and sends it out on another channel. So this could be used for other people to watch real-time updates of where the canoes are on a map.
think I remember reading Bob had used this for his APRS satellites he launched, when he was working at the Naval Academy.
Yeah, that's related. Not exactly the same, but related.
Actually, I think he did launch one with this design on it. John, I had an argument with him one day, and I told him how much easier your way of doing it was than his way. And so I know that at least one satellite had this capability.
We've done that with Bob on some races around Annapolis. And quite frankly, it got to be sort of awkward because most of us had good APRS radios anyway. So I wouldn't say it fell by the wayside, but it wasn't really a practical application for what we were doing because we were better equipped. So it kind of fell by the wayside here. But we understood how it worked. We did make it work to show that it did, but we didn't stick with it.
Yeah, we had a similar experience. We used it for several years in our group, and the problem was we ran out of numbers. We can only do up to 100 on here, from 0 to 99. Any more than that, and you just don't have any way of transmitting it, and without a much longer transmission involved and a lot more numbers being hit, which was, of course, the problem in the first place. You can send a lot of information through Aprs-Tt, but you're going to have to expand how many you have to type in the first place, and knowing what you're typing in is what becomes difficult.
Yeah, there's a lot of chance for human error in there between the lip and the receiver.
Yeah, but yeah, the idea is if you don't have, I mean, ideally it would be best for everyone to have fancy APRS transmission equipment, but it makes it possible, if not ideal, for people with just a touch tone pad to enter information into the system. Okay, moving along, you know what a digipeater is. The interesting thing here is that Direwolf can connect to multiple radios, and you can set up routing for any combination of to and from channel with different filtering for each of those paths. So a gateway connects to the Aprs-IS servers. And some people think that the purpose of it is so that you can use a web browser to look at the worldwide APRS activity, but they're really missing the boat. The real intention of this is it can connect disjoint radio networks so that you could have an HT in one part of the world, go across the network, pop out on another radio network on the other side of the world, and then talk to people there. Well, send messages to people. And here's an example of how it would work. Supposing ham1 wanted to send a message that is the special APRS meaning of message to ham2, it would get sent over the radio, sent through the gateway station to the servers, and then the servers would say, where has ham2 been heard recently? And then it forwards the message to the iGate stations near where ham2 had been heard recently. And then optionally, an automatic acknowledgement can be sent back, or the user can send a reply message, and the same thing. It gets here and it says, oh, where was ham1 heard recently? And it could send it out to multiple gateway stations going back to the original station. Some people set up receive-only iGate stations, which go from the RF to the internet. And unfortunately, that breaks the original intent of being a two-way communication mechanism.
This essentially was, in the early days, poor man's cellular roaming network, the way the protocol for the IS servers worked. Whereas it would have, the location and locate people and route the traffic back out to RF and the more logical places. And
Yeah, I mean, the system actually works well. Okay, there are different application interfaces for client applications. Okay, we've talked quite a bit about the KISS interface, where information just gets pretty much pushed right through, encapsulated with HDLC, and off it goes. For connected mode operation, that's where you connect to a specific station. There's a protocol engine in here which will add sequence numbers to the information frames. It'll send acknowledgements and do automatic retries. So it gives you a reliable transport mechanism, or you can get back an error notification that it failed. Now that's only available in the HEW network interface. And of course, you can have many applications connected at the same time. Okay. So when I started this project, I had no academic or professional experience in digital signal processing. So I had absolutely no clue on how to build a demodulator and software. So this is what our most common signal looks like, right? The audio frequency shift keying, where we switch between two different audio tones to represent 1 or 0 bits. So it's easy enough to generate. And then on the receiving end, the demodulator has to decide, well, do we have this low tone or do we have this high tone? And this is one way you can do it. There are other ways. You can have a bandpass filter for each of the frequencies, and then take the amplitude, low pass filter it, so you can get the data, but not the carrier tone, and then compare and see which is greater. Now, back in the old days, you could use RC or active filters for these bandpass filters, but now we can just do it in software. So after a lot of experimenting, I was really thrilled that I was able to decode some perfect signals. But when I connected it up to the radio and compared it with a normal TNC, I was soon disappointed because it really didn't work too well. So I started a quest to figure out why. What was different? Why were real signals not the same as the ideal signals? So WA8LMF did a great service to the ham radio community by gathering a bunch of actual Aprs traffic. He drove around Los Angeles during the afternoon rush hour when the frequency was like completely saturated. Okay, and of course, since he was moving, it was always changing what stations he heard better. There was under deviation, over deviation. There was stations stomping on each other. And when you look at some of them, there's some really weird stuff in there, and you have to scratch your head and you say, where did that come from? So I think you'd really enjoy looking at this document in the documentation section. You'll see plots of many of the signals found there. And,
I actually came across the ISO of this not too long ago.
yeah, so on track one of, he distributed an ISO image that you could then burn to a CD. And then what I did is I ripped the tracks into audio files so I could play them over and over. So I could repeat tests easily and faster than real time. So the track one used the flat audio. So it was the most accurate representation of what was actually on the radio. And then he applied, afterwards, he applied de-emphasis to mimic a typical receiver, and that was track two. Unfortunately, he did it wrong. He did 12 dB per octave instead of 6. So it's not as useful as it could have been. But anyhow, this has become the de facto standard for people measuring demodulator performance. So many people have tested different TNCs and published how many packets could be received. And I've split them into two groups here. Some of these are software, these are traditional hardware TNCs, hardware, software. And you can probably see a pattern here, but when you plot a little bar graph, it really jumps out at you. So the modem chips, do somewhere, like 700 to 900 some frames decoded. The early software attempts did very poorly. And you will find articles where people say you absolutely must use a hardware modem for good results because the software is garbage. But that's outdated information. The more recent software modems outperform the hardware modems. And however, the tarnished reputation still endures because there's a lot of outdated information out there.
Data packet information on the internet, absolutely.
I didn't catch that. It was too quiet.
I'm sorry, I said there's a lot of outdated packet information on the internet.
Yeah, most of it's from like 20 years ago.
Yeah.
So we are generally using VHF FM transceivers that are designed for voice. They are not designed for data. And transmitters reshape the audio with something called pre-emphasis, which means that they increase the gain as the frequency goes up. So basically a high pass filter. And the standard is supposed to be 6 dB per octave, which means as you double the frequency, you're going to double the voltage amplitude. And then on the receiver end, it's supposed to do the exact opposite. And in theory, it should cancel out, but in practice, it doesn't work that well. So for voice, it doesn't matter much, but if you're using modems, they're a little fussier. So the biggest problems occur is when you have a mismatch between the transmitter and receiver. So if you're using flat audio on transmit, and you're using de-emphasis on the receiver, the higher frequencies are decreased in amplitude, okay? Now this is this is a genuine signal recorded off the air. I should probably do an artificial I should probably generate something artificially to make it more pronounced, but you can see that the low frequency is this amplitude, and then higher frequency is lower amplitude. And here's the opposite case, where if you use the microphone input, you get the pre-emphasis, making the higher frequencies stronger. And if you have the flat audio on receive, higher frequency, higher amplitude. So this makes the demodulator less reliable. So it'll work most of the time, but you start getting into some of the marginal signals, it just doesn't work too well. So the first idea I had was applying automatic gain control, and it was improved. But of course, the AGC takes time to adapt. And if there's a little noise blast, that would throw it off and it's all over. So a brute force approach to this would be to have 3 or more complete demodulators, and then you put a low pass filter in front of one, put a high pass filter in front of one, and then you feed this off to 3 separate decoders, and then you just eliminate any duplicates between them. But of course, this is very computationally intensive. So I came up with a different way to reduce the amount of computation. Okay, this part's very expensive. Lots of calculations. So after extracting the amplitudes, I make one of them either weaker or stronger before feeding it into a bunch of comparators. And all the best software TNCs use some variation on this approach, where they have 3 or more demodulators all running in parallel, fine-tuned for the imbalance of the amplitudes of the 2 tones. So what do you do if your radio signal isn't quite strong enough to get through? It's just marginal. More power, you could move to higher ground, get a better antenna. Sometimes those aren't options. Another technique is you can add redundant information to the message so it'll still get through even if some small pieces of it are missing. Okay, this is a very common technique, used all over. It's used in radio communication, digital video, QR codes, disk drives. It's even used in CDs and DVDs, because you may have noticed you can have a couple scratches and it still works perfectly as if the scratch wasn't there. It's because there's redundant information. So it can reconstruct the original signal, even though some of it has been corrupted. So the STENSAT group came up with a very clever way of adding forward error correction while maintaining complete backward interoperability with normal AX25. So this, this larger block of information starts off with a carefully constructed code of 64 bits, which introduces the block of information. It has the normal AX25 frame and then some parity check information. So if you have a normal AX25 system, it just sees this part and the others are just discarded as random noise. But if you have a system that recognizes the entire block, you can have a very powerful error correction. So the 64-bit tag values at the beginning are very carefully constructed so that there's a maximum number of differences between them. So you can tolerate a few of the bits being wrong and still not mistake it for a different code. And then each of these represents a different format for different numbers of data bytes and different numbers of check bytes. Now, the one thing you want to notice here is that the number of bytes that can be corrected is 1/2 the number of the check bytes. Right, so if you have 16 check bytes, 8 bytes can be repaired, or if you have more overhead with 64 check bytes, 32 can be repaired. So very powerful. I did a little experiment with 1,000 APRS frames and introduced a controlled bit error rate. And when the bit error rate was about 1 out of 1,000, half the frames were lost. And then, 1 out of 100, it was completely useless. But with the FX25, it just kept going and going and going with a much larger bit error rate. And you notice here, if we have the 64 check bytes, it keeps going the longest, but there's the most overhead.
And is that because you're using UI frames versus connected frames? Is that one of the reasons for the improvements?
Well, the reason for the improvement is there's a mathematical process, okay, that on the transmitting end, you take, on the transmitting end, you take this original data, and then there's this mathematical process that comes out with a smaller redundant information. So if, let's say, a bunch of bytes here got clobbered by a burst of noise, this additional redundant information can be used to regenerate those missing bytes.
All right, I guess maybe I asked my question wrong. Would you see that type of performance improvement on connected packet instead of UI,
Okay. Next slide. So I did it for connected packet.
Look at that.
What a coincidence. So here we have normal, this is the throughput in terms of bytes per second for normal AX25. And of course, as the bit error rate goes up, more packets get lost, so there's more retries, so the throughput goes down. And again, we see it becomes useless at a bit error rate of about 1 out of 1,000. And for the FX25, there's more overhead, so the maximum throughput is lower, but it keeps going. As the error rate increases, it just keeps going much longer because the errors can be corrected. And again, the strength of the error correction depends on the number of the check bytes added. So 16 gets you this far, 32, 64.
Does the check bytes get altered by the size of the packet or the packet length? Or is that just something that you set when you set up your FX25?
Okay, well, the way I implemented it, you can either have automatic selection based on the size of the packet, or you can force it.
Okay.
So let's say you had 80 bytes in your normal frame, your normal AX25. If you put into automatic mode, it would have to pick something where this number is bigger than 80. And then I change the number of check bytes depending on the size, because the longer the frame, the higher the probability of it getting clobbered. So I add more check bytes. Or there's also an option where you can force the number of check bytes. So you can always get the maximum if you want to. So recently I added IL2P. I don't know if you've heard of that. It's a different forward error correction scheme used by the Nino TNC. And there's less overhead, but it's not compatible with the old AX25, so there's no interoperability. So I think that's about it.
Can you field a question?
Yeah,
I threw it into the chat. Do you know what all APRS software besides Direwolf and or hardware actually implements the FX25?
yeah. Shortly after, like a week after I did it, the UZ7HO sound modem did the same thing. And I did interoperability tests, and they both talk to each other nicely. And that's in the documentation. There's a document talking about FX25. So near the end of it, I talk about interoperability, and I show some samples that came from satellites and showed that they could be decoded properly. And I also sent information back and forth between Direwolf and the UZ7HO.
Okay, so, but this is Lynn, KJ4ERJ, the author of APRS-IS32.
Yep.
If I'm talking just to a KISS modem, unfortunately, I can't really put anything around my AX25 packet. So you have to be either implementing a sound card modem or something hardware-wise that's talking direct to the bit banging to pull off FX25. Is that correct?
Yeah, this is completely in the TNC. The application still sees the same KISS and doesn't know if it's regular AX25 or FX25 or IL2P.
That's what I thought. Thank you.
Right. The TNC adds all the extra overhead and error correction. The application doesn't know the difference.
John, can you talk a little bit more about IL2P? It's intriguing. Obviously, it doesn't work well on the APRS channel because it needs to be AX25 compatible. But is IL2P more efficient than FX25?
Yeah. I don't have information available, but yeah, rather. Yeah, if you want all the details, I urge you to go look up the Nino TNC, Nino TNC.
I've got two of them sitting here on my bench that I have to play with. So
okay.
And very interesting to hear that the Direwolf's got it as well. But
yeah, it's completely interoperable. I've been sending stuff back and forth.
Excellent.
So it uses a different scheme rather than let me explain. Okay, so it starts off with, I think it was a 24-bit tag, always the same. Then there's a little header. I think it's like 11 bytes that has the source and destination call and information about how much is to follow in multiple blocks. And all those blocks are the minimum size, so you don't have wasted space. So let's say, for example, here, using my example, if I needed to send 80 bytes, I would end up sending a block of 128 bytes and then filling in, 48 of them with zeros. So that would just be wasted time. So it is more efficient.
But as you mentioned, it's not backwards compatible, so they can't
Right.
just on the same channel. Or they can't talk to each other on the same channel, I should say.
Yeah, right.
Evening, John. You've described a number of advanced features that I, for one, didn't know about. Are all of this covered in the manual for Direwolf, or is there additional documentation?
Yeah. Yeah, the user guide is sort of like a reference to the command line options and the contents of the configuration file. You really need to go look at all the other files in the documentation directory.
Mhm.
There's one talking about the TNC test CD. There's another talking about FX25, another one talking about PSK. There's another one in there talking about the emergency alert system. So there's a lot in there. It's all written down somewhere, but it might take
There
you
you
time
go.
to find.
A lot of good work, John. Thank you.
Thank you.
John, another question for you relative to the Golden Packet event. If we're to use the Direwolf and we're, experimenting with a couple of hardware devices that implement Direwolf, if we were to implement amongst ourselves for the Golden Packet event, FX25 on these events, would we see performance enhancements over what the Kenwood radios are doing now? And more specifically at 9600, obviously, is the interesting part. Would we get any performance enhancement because of that?
Yeah, because if you're missing a few bits or bytes, they can be filled in. So for marginal conditions, yeah, it will give you more range.
Did you guys all get that? That's a thought process change.
Yeah, and it forces, one of the things we're railing against is the recommendation it'd be D710s. And now we're going to say we're going to use FX25, which has 2 implementations.
Well, the implementation is in the software mode.
Right. You're going to be using a Direwolf station or a UZ7HO, whatever it is, sound modem.
But a lot of the hardware solutions we're looking at, such as the DigiPi, or a lot of them tend to be Raspberry Pi type solutions. We're using that software package in there. And, if we're trying to get better performance and more success out of the Golden Packet event, or do we just want to do as good as we did with Kenwood? That's my thought philosophy there. And
I'm all for it.
Kenwood is my question.
But
Yeah,
we could
it
mix and
definitely
match,
would be.
can't we? If there's a D710 in the link, it'll ignore the FEC packets, will it not? Or
Yes.
FEC bytes, will it not? So it'll receive the signal, it just won't have forward error correcting. It'll transmit the signal without forward error correcting, but the next Direwolf or UZ7HO station that picks it up will move it on with forward error correcting.
Right, it's completely interoperable. That's the beauty of it.
Yeah.
Yeah, that is a very seriously major feature.
So that you could literally turn it on those stations which have it and improve the quality of their link. And if the person's with a D710, it's the way we've always been doing it.
That's interesting. It may turn out that these start performing better than the litmus test of the Kenwood radios, right?
It's already better than Kenwood.
It's certainly better at receiving than Kenwood.
Well, what we're saying is,
We're starting to, I think we're assuming that will probably be the case at this point.
but we're also going to have to do it at an appliance operator level. It's
Yeah.
got to be an appliance operator device,
Yeah,
John. That's it.
absolutely.
We're
That's
struggling
what
with.
Don is, that's what Don and John and Lynn have been working on.
In real life, if out here in the world, not outside the Golden Packet event, if we have digipeaters and iGates set up using FX25 and the mobile units are still D710s and such like, the iGates and digipeaters can actually improve the operation of the whole network then, is that correct?
Only if the iGates and digipeaters are only talking to themselves. if they're trying to receive or transmit to call it a legacy station like a D710, the FX25 is just occupying bandwidth for no purpose.
Okay, so the D710 cannot translate the FX25 and read it then, is that correct?
It will ignore the header and trailer wrappers of the error correction, but it will process the AX25 packet that's embedded in the center of it. So it's not going to improve the network unless the stations that are transmitting and receiving the packet both have FX25 capability.
Okay, so we're not excluding our mobile units that we have right now, but as they come along, whatever it is we do with them, then we'll improve our network capability in real life here as we're looking at vehicles traveling down the road, talking to them.
Correct. That we're not pushing out the Kenwoods. The Kenwoods will work as they always have. We can add it to these other stations. If someone's broadcasting the FX25 packet, the Kenwoods or legacy type APRS devices will just ignore the error correction, and they will not get any benefit from the forward error correction. So it'll just be the same as it ever was.
And I get using the FX25 system will put a better set of data into the APRS-IS that might have a better chance of being transmitted through there without error. Is that correct?
No, and not unless the station that's going into the iGate has broadcasted an FX25 packet as well.
Okay.
Now, we will do, this will have a cost in bandwidth, but at least in our areas, when I'm looking at the loading on the APRS channels, we're not bandwidth constrained, so there doesn't seem to be a big downside, at least in our area, for adding FX25 if our equipment's capable of doing it.
On a UI packets, I don't think it's a big cost. I think you'll notice it more in a connected packet network than you will in an APRS UI frame network.
Yeah,
John,
but you introduce another problem when we start talking about the connected networks. That's a different problem.
yeah, John, what is the percentage overhead of a typical APRS packet to wrap it in FX25?
You could probably get an idea of it from here.
Actually, the table that had the bytes that were being added is probably easier to figure it out from. So
Yeah.
there, a typical APRS packet is what, 64 to 128 bytes?
Okay, so supposing supposing the AX25 packet was 64 bytes, that includes the flag at each end and the CRC.
And the digipeater path, which adds up 7 bytes per entry. So we got 14 bytes right there at the beginning guaranteed for the source and destination packet address. However many digipeater pads are in there, let's call it 3 or 4. So that's a total of 6 times 7. We got 42 bytes right there plus the payload. Yeah, 64 to 128 bytes of AX25. And we're going to add, if I read here right,
16.
a tag number, a correlation value, and check bytes.
8, 16. See, the thing is you have to round it up to one of these numbers.
So we're going to put padding at the end of the AX25 packet to make it 128 bytes.
Yeah,
Okay, so if we had, say, 100 byte packet, we're going to add 28 bytes plus your correlation tag plus your check bytes. Do I understand it right?
right.
So your correlation is how many bytes?
8.
So 8 and 16 is 24. So we're going to add 24 bytes of absolute overhead and AX25 packet padding to make it 128 bytes or 64 bytes. So if we had a 65 byte APRS AX25 packet, we're going to add 63 plus 24 bytes to that packet. Is that a true statement?
Yes, that's how I
So
would.
yeah, we're talking a lot of overhead here because not so much because of the correlation tag and the check bytes, but that rounding factor forcing our AX25 packets up to the right number of data bytes.
Lynn, there's a mitigating factor here in that we don't occupy the channel totally with at the transmission of data. Typically at the start of the packet, don't we put a little dead air in and at the end? In other words, we don't key the transmitter or immediately send the first bit because the receiving station may not be able to respond that quickly to the first bit. So in a regular X.25, how much overhead is lost, particularly at 9600 baud, or for lack of a better word, for dead air to allow for latency on the channel?
We're still going to have that in the FX25 because we still have to account for they need to see the correlation tag value. So that front porch delay is still going to be there.
So absolutely. But if the front porch delay is much greater than, say, the time to send to 16 check bytes, right? The percentage impact would be different.
So
yes,
then,
it's a very hard number to calculate.
but so the question also stands is that if we're only implementing this not on our standard APRS network, but on the golden packet network where we're typically off on a clean frequency and not competing with all the hidden transmitter, packet collisions at the digipeaters and all that stuff, do we see a different performance increase over the regular packet channel? So, I'm just throwing that out there. I don't know the numbers, and but you're bringing up good points, and the key is that does it give us better, especially as we push for the 9600 baud? Does it give us better success ratio, on the decoded 9600 baud packets? I mean, the fact of the matter is, as long as we get people up to the hilltops, we've proven time and time again that the 1200 baud packets go all up and down the Appalachian range, no problem. We're not doing anything new there, and going back to 1200 baud to prove that we can still do it, I don't think is buying us anything. Can we start to get more throughput? Can we do 9600 baud? And do these tools in the toolbox cause us to have better success? So that's kind of my thought in the whole effort of these knowledge sessions and such.
Well, I can say that it will definitely give better success from my limited understanding from having arrived late. And I apologize for that, John. I really wanted to be here on time, but I had a conflict this evening. So I will be watching the recording. So it will definitely increase our success. I have not personally been in one of the center stations on the Appalachian chain to know how busy the channel is there in the middle. I was at Springer one year, but it was the first year that the golden packet ever happened, and the frequency was absolutely idle. So this overhead is a totally non-issue. But when all the stations are online and they're all beaconing, that's actually one reason that the newer year's suggestion is to reduce the beaconing rate of the center stations because it's making so much traffic through the center of the chain and going out both ways. So it will definitely improve the low signal decodability so that more packets will actually start going on the chain, which is going to increase the channel utilization, where right now we know for a fact that you can hear a packet that doesn't decode.
Lynn, you just brought up an interesting thought as you said that. Since we've all got GPSs in all these devices, have we looked at time slotting these? We've got synchronized time sources. Everybody's got a GPS. Why don't we time slot the packets?
You can time slot the originated packets, but that doesn't help you handle the digipeat delays coming up through the chain.
But if the digipeaters can store and forward on the time slot, wouldn't that solve some of that problem?
Oh, now we're talking some serious networking
Well, I mean,
software that doesn't exist
always
yet.
had a problem with this golden packet event with Bob and I. We've always argued for the fact that you're never going to be doing a daisy chain network if you want to make an East Coast network. You're going to make point-to-point links and have nodes. So that's always been a fundamental problem in this whole drill anyways, but I lost that battle. And, but time slotting, meaning dynamic polling, DAMA type things like FlexNet does and things like that. If you do DAMA polling and things of that nature, and if each of the stations gets their time slot, and maybe you have 2 or 3 DAMA masters along the trail, you could make this network scream.
I don't know enough about all the technologies you just rattled off, but yes, if you've got stations that are coordinating on their transmits and not just transmitting when they hear the frequency clear, you're definitely going to increase the throughput.
Yeah,
But are you going to end up with a network that can deploy ad hoc in a situation where people only happen to have APRS hardware in an emergency situation?
Probably not. Right, and then, but if someone can kind of come up with, hey, this gets us closer there. I'm just thinking, we've all got GPSs in the units. They've all got a synchronized time source. Time slotting, if somebody who's smarter than I am in the math can look at the number of stations, can look at the number of permutations you can do in a time slot and figure out which ones can transmit on which slot, I'm wondering if that isn't a possibility. It makes my head hurt thinking about the math on it.
Well, I was going to say, let's put that on the agenda for 2024.
That's fine. Just throwing the idea out there. Maybe John.
I like it.
For my gross experience in the middle of the chain at Maryland Mountain 7 for several years, I had, my D710 was the digipeater there. And I was also monitoring with a listen-only APRS IS-32 station hooked to my computer. And I was watching signals come by, and I caught very, very few packet collisions. I heard everything that came to me and transmitted it along, and it worked fine. I don't think we had a lot, so much traffic that we were having packet collisions along APRS, along the golden packet. For what we were doing at the time, that was not a problem. Now, if we're going to do other things with that link or that network, then it's going to be a different story. But I did not hear a cacophony up there at Maryland Mountains.
Gordon, you bring up a great point. If any of you haven't done it, and this is where I love Lynn software for this, is that I love to run my APRS on RF only, because I hear about 6 to 10 digipeaters directly from my house, and I'm listening from Pittsburgh to Boston from RF only. I can see somebody with a bad path setting because that software draws the lines when you're watching the packets hop around. Nobody else does that. Actually, another program, Radio Mobile by Roger Kude, when you played with the APRS plugin to that propagation software, also did that. And I would highly encourage anyone to just sit there and watch the packet network, the ping-ponging, the bad paths, where you're getting 2 digipeaters that you're hearing that are at the end of a wide 2 path. That is probably one of the bigger helps to anybody to try to visualize what the network's doing and the hidden transmitter syndrome.
Yeah, one of my pet peeves in the actual network out there, we have stations that are sending a packet path of wide 1.1, wide 2.2, wide 3.3, wide 1.3, and all that stuff, and they are lighting the entire northeastern United States with their packets. This is not a DX game; it's a communications game, and I'm not going to be the APRS cop, but somewhere along the way, we need to get the word out to them so the network as we see it right now is not going to be swamped. I'm in Baltimore. Brian is lucky to be in Cooperstown. And I've talked to Brian on the phone from Mount Oceantha several years ago. But, that's I would say the extent of our communications, but I know exactly where he is because I used to live in Stanford for most of my life. But that is not a network up there that's swamped with stuff. But here around Baltimore, Washington, I copy the all the packets on my APRS IS-32 and I print them out, and I see these things because the APRS-FI network is not seeing them. It's only recording the first packet that it hears, but I see everything that comes to me and it's garbage. I mean, there are people who are just swamping this thing down here. That's a whole different story.
You absolutely do see that. The other interesting thing that helped you visualize it too, although not quite the same, was on UI View, and they had there was a plugin for that allowed you to look at which digipeaters were hearing which stations, and it would make a combined map. That was also an interesting visualization tool. But Gordon, you're absolutely right. But at the same point too, those paths that you're describing, aren't the wide 2-2 digi supposed to filter those out and lop them off at 2 hops? I thought
I do, but not everybody does.
But Lynn, I gotta tell you, man, the packet hops visualization on the map, and most people don't see that because they hook up to the internet. And it probably would be cool for you to make a little animation video or something to go on the website to show people that feature, because it's a cool feature that teaches people really fast.
It absolutely is. And I'll see if I can put together a screen cap of it for the presentation next month, actually, when I'll be talking about. Oh, wait, next month I'm talking about why we're setting Kenwoods up the way we set up Kenwoods.
Gives
Right,
you more
John?
time to get the animation done then.
But yeah, so I gather you run the.
Sorry, I was
the
looking
view
for the
paths
mute.
with-
Yes, that is what you, but you can adapt it a little bit.
Okay, so you run it with the flash setting on the showed paths? Brian?
Whatever it does, it just hops across my screen all the time. I'm watching.
Yeah, okay. Well, there's a setting I really like to do. It's called flash. It just kind of flashes the things out there and then they disappear.
Yeah, that's what I'm doing it, yeah.
You know that Aprs-Tt also gives a raw RF feed
Yeah, you
to my
mentioned-
server.
Yeah, you mentioned that.
So I can actually bring up a map of the entire planet and see real-time RF tracking for every packet captured by an Aprs-Tt iGate.
Will that
Not,
go so fast that you can't really understand it if you zoom in or not?
oh, if you zoom in, it's totally understandable. When you're zoomed out to the whole planet level, no, not so much.
That's fine.
Do you think maybe we could cooperate or collaborate a little bit on this? Because I'm not an expert in it, but I know what I see. Maybe write an article for QST and explain to people what they're doing, because they think they're not. They go on to APRSFI and say, okay, you know, my packet was picked up by the station, but it doesn't show the other 5 and 10 that were digipeating them and causing all that confusion and network congestion.
Or it doesn't show the collisions where it never went anywhere.
Exactly.
Yeah, those are the ones you can only hear by ear. We can't show those.
Well, you know, that's funny. You know, I work obviously as a commercial wireless engineer, and these guys, when they're building Wi-Fi networks and hidden transmitter syndromes, and they're like, how do you visualize all this? I mean, I've been doing this stuff at 1,200 baud packets, standing at hilltops, listening to the packet collisions and listening to the hidden transmitter syndrome. At 1,200 baud, you can hear it. At you know, 50, 60, 70 meg, you know, you're never going to hear that. It's just static noise. So
Right.
my 30 years of packet radio have really helped my wireless networking development.
Yeah, well, thank you for the compliment of the path visualization. I'll see if I can weave that into January.
Yeah, that is something that everybody, as Gordon mentioned, everybody in APRS doesn't understand. No, hidden transmitter syndrome, unless you've stood on a hill and heard both stations transmitting at once, it never sinks in your head. It doesn't. There's never been a good explanation of it.
So I don't know whose website it is, but there's a site that Bob links to off of aprs.org where somebody has the RF path analysis for most of the current sites, some older sites that we don't use anymore. But I actually started building us an official wiki. Surprise, surprise.
I could run those.
So we will have a site, atgp.wiki, soon, and I have all of the RF path analysis stuff already incorporated, but I would love to get something more modern.
There's 2 tools that are frequently used. One of them is
Great,
Splat,
great.
which is a Linux package, and then the other one is Radio Mobile by Roger Kude, who's a handy.
Yeah, Radio Mobile is a pain in the ass to use.
Oh,
though.
it's not. I mean, I've been using it for 30 plus years. Once you get to know it, I can blow through that all day long, but I use it every day.
I would love to spend some time with you on it.
Well, if I can get the end coordinates for a path, you know, just give me the frequency, the height, and
Yeah.
the 2 coordinates, I can run path studies all day long. I do it for the EastNet packet group as well, as we're trying to build node links back together. So I throw them together all the time.
I can do that. I've got all that stuff logged.
Hi, this is John Tarwax. I have a Direwolf question for John.
Yeah, and by the way, I mean, we're already like half hour over, so I mean, I don't know time-wise what you guys got going, but I mean, we can keep going for a few more minutes.
Is John still here?
Still here?
2 things, John. and they're both probably out of scope for this call. But one of the issues I had is trying to do software development with Direwolf. And we had the issue on the Raspberry Pi where we went to the new version of the operating system and then the version of hamlib that I wanted to use because the package distributes an older version. And then like, how do I had to rebuild it on a different version of the operating system and that whole software development process. If there's some resources around that, or you're ever doing a session on that, I would love to get some guidance from you on that. And I know it's out of scope for this call, but I'd love some resources on that. And the second thing I would love to hear your thoughts on sometime is we focused on X.25 protocol, but there are a lot of new protocols being developed like FT8, like PSK31. And I would love to hear your thoughts sometime on how do we get new protocols into Direwolf. And if you were going to be developing a protocol from scratch today, would you do it differently? How would you approach that? And
Those are the only
I know these
questions.
are out of scope for this call, but that's information I'd love to get from you.
John, how about just the future of Direwolf? What do you have in mind for it going forward, if anything?
It's a hobby time activity, so I just do whatever seems interesting. There's not a particular product roadmap like a commercial product where this is what we're going to do a year from now, 2 years from now. It's whatever I feel like doing.
Any hints of what you're seeing now, John, that interests you?
I scribbled down time slotting for beacons.
Okay, thank you.
Okay, in the GitHub issues section, there's just loads and loads and loads of stuff that people suggest. I need to make a pass through that and figure out, what's interesting and or useful.
On the topic of time slotting, John, I think it was, I don't know how many trackers I've got. I think it was the Open Tracker from Argent Data. I think their software had an option for having some very rudimentary time slotting, basically just when you weren't using carrier detection. But there was no synchronized time source in those devices. So that was rudimentary and, haphazard and lucky at best. But I'm thinking if we can use the timing pulse from the GPSs, that we might have a better rate of success of some sort of time slotting. Because how many sites do we have up and down the chain, Jeff? Are we at 14?
15.
15. So, divide it by 15. Somebody's got to do the math of especially for the middle station, what are the opportunities of collisions or factorials of collisions as you hop farther down the chain? Yeah, my head's third. I should have paid more attention to math, right? Some of your math gearheads are probably like, oh yeah, that factors out to it's 10 to the 15th power, right? Maybe it's as simple as that. No, 10 to the 15th factorial. That sounds about right, but I know too much to be dangerous.
But you're really only hearing stations typically a couple of hops away from you. You're not hearing the whole chain.
True. Right. Yeah. See.
Yeah, but you are still wanting to pass through the packets that have been digipeated down the chain, and how to fit the time slotting into the digipete repeating. Because my understanding of time slotting is it's primarily focused on the source station when it's going to send its beacon.
The thing that you would have to do about the digipeating, Lynn, is just buffer it and not repeat it until it's your time slot. Don't just quickly.
Like I said, when I was in the middle at Maryland Mountains, I was looking at all the packets that were going by that I was recording on my Aprs-Tt IS32 receiver. and I was listening to the audio at the same time. I did not hear a lot of packet collisions because if I heard a packet on our frequency and it didn't show up on my computer, okay, well, that was a collision. But I was receiving and recording practically every packet that I heard come by me both directions.
Yeah, if the time slot could take the position of, I'll just assume there's a carrier detect until my time slot comes up, and then I broadcast. If the digipeater could function, like I said, I'm just going to be here making people's head hurt. That's.
But the time slot, what the time slot allows us to do is avoid collisions. Am I correct?
Yes, you try to avoid transmitting over top when somebody else occupies that time slot.
Sure.
But the digipeater can't be set up to then, oh, as soon as I hear something, I got open airtime, I'll read a digipeat. You got to stop it from doing that.
Yeah. Every station would have to have its time slot. But I believe Gordon was saying, and it matches my memory, I'm not hearing a lot of collisions as I recall in my location when I'm in the chain or out for golden packet.
Right.
I don't think our packet rate, even in the center, is high enough that we're developing a lot of collisions or even chewing up all that much of the channel bandwidth.
Right. So if you take 60 seconds, for example, and you divide that by 15, right? 60 divided by 15. So you got four seconds per time slot that someone could send their payload, whether it's a digipeated or a transmitted payload.
I don't think that math works with the front porch delays and everything else that goes on in there.
Okay, well, let's say you take 20% off or whatever. Let's say it's half of that. Say it's a 2 second. How many times do we send more than a 2 second long packet? Not very often. Or we tell the software to not, chop the packet into another payload if it's more than 2 seconds. That's kind of the principle behind DAMA. DAMA is demand access, multiple access. All of a sudden we can't hear you, Lynn. I don't know if you muted or what. Or maybe we ran out of time. Maybe everybody shut me out.
No,
I hear you.
No hearing.
I think the problem we're getting is primarily bad packets, though, not collision packets. I think that's our immediate problem. I could be wrong. But
Well,
at least that's my perception.
Well, that would eliminate one of the possibilities of a bad packet. And, the problem is that you don't know if a bad packet is bad if you're not hearing, if your end isn't hearing a collision on the opposite end that you're trying to send to.
Well, from working from the shack and helping people try to figure out why we're not seeing across the given link, most of the time they just don't have enough signal strength to dig the packet out of the soup. They're hearing the packet burst and they're not seeing a decode. It's not a collision packet. It's just their antenna is not quite in the right place to handle a good signal across that particular link.
Which brings up a good topic that if it isn't already on the list, Jeff, we should probably spend one knowledge session on antennas, coax, feed line, especially at UHF.
Absolutely.
And adapters.
UHF or VHF?
UHF. UHF, you can get.
Oh, yeah, for the secondary comm channel. Okay.
That's going to be just as much an issue if, like Lynn said, not enough signal, one poor quality PL259, which you really shouldn't be using at UHF, but the manufacturers keep putting the connectors on. You can have 3 dB loss on a bad PL259 connector.
Yes, you can.
And that's not only 3 dB loss in transmit power, but 3 dB loss in the receive signal you've got coming from your antenna down to your radio. It goes both ways. Or just a poor quality, or a kinked feed line will work okay at 2 meters, but sometimes not at 440 because that's why you've got different losses per different frequencies. So that stuff all adds up. So it's just another knowledge topic that we could hit in the future if we don't have one.
Yeah, guys, I mean, just out of respect for our speaker, John, I mean, we've kept him another 40 minutes beyond. So I figured maybe we can wrap things up.
All I can say, John, is wow.
Yes, yeah. Agreed.
I'll second that.
And thank you
Big
for
thank you.
spending so much time after with us.
Great project and great product you've got, John. It's amazing.
And John, author to author, isn't it great to just work on what tweaks your fancy this week?
Hey,
I think
as
each-
basically a user, I want to tell you how much I appreciate being allowed into this conversation here, because the golden packet is a whole lot more than just passing a packet from Springer Mountain up to Katahdin. It's developing the state of the art, and if we can do that, and you can do it for us users, we really appreciate that.
I don't know if we lost John. He's been
I'm
quiet.
still here. Yeah, it's yeah, there's a lot of there's a lot of links in the chain and a lot of teamwork to make it work.
Excellent.
John, I assume that you are compatible with the Bullseye at this time?
Compatible with what?
The new the new Raspberry Pi and
The new
Debian-
Raspberry Pi operating system?
I've compiled it on Bullseye. There are a couple compiler warnings, which
Sure.
are nothing to worry about. But you always get that new compiler always gives you more warnings. It basically works. I haven't tried it on the air yet.
I think DigiPi 1.6 is Bullseye, is it not?
It is. Yeah. it is.
So it's running there as best I can tell.
What is your primary development platform, John?
Mostly Windows 10. And then I and then I download it to a Raspberry Pi and see if it works there. And then once in a great while, I put it on the Macintosh and see if it works there. And I do have an old Linux system somewhere, which I haven't touched for a long time. I figure if it works on a Raspberry Pi, it'll work on a big computer.
Yeah, one thing you may in the future find interesting is under Windows 11, the Windows subsystem for Linux is much, much better than under Windows 10.
My computer's too old to run it, so
Okay,
I won't be seeing
that's what you do. So are you using Visual C as your compiler?
No, I'm using GCC.
DCC. Because obviously if we're trying to do development, if we're using the same platform you are, hopefully, in other words, that would eliminate other kinds of errors you don't want to hear about. And so have you documented somewhere your reference build environment?
Yeah, it's in the user guide.
Thank you.
Yeah, it's a little tricky on Windows because you have to set up Cygwin and install the Minji compilers, which are really a special build of GCC that makes native Windows code. But it simplifies things to use the same compiler everywhere.
Right.
All right, guys, let's close it up.
Thank you very much.
Thank you so much,
chance.
John.
We're good. Thank you
Big
so much.
thanks from here,
Thanks
John.
for organizing it, Jeff.
Have a great night, everybody.
Good night all, and have a happy and safe holiday.
Yes. Same to you guys.
73.
Thank you all.
Cheers.
Bye.
Bye.